Okay, thank you. So last time I went over Ambrosio-Kirchheim, so let me just review from Ambrosio-Kirchheim. There was this notion of integral current, right? So they have a current on metric spaces. Is a T which acts on F pi 1 through pi m. And there were some rules. One of them was the additivity rules. We had, anyway, there were a number of properties that were required on this T, and then they proved a number of theorems, which included things like obtaining the chain rule, and they obtained the notion of boundary and all these notions that you would expect this T to have. An example always to keep in mind, the integral current case, interrectifiable current case is has the form that T of F pi 1 to pi m is a sum of theta i's integration over a i's of let's say F following phi I, D pi 1 following phi I, wedge D pi m following phi I, where this is countable sum. The theta i's will be integer valued and positive, and the phi i's are by Lipschitz. And they go from AI's sitting in Rm to Z, and these are Borel sets. Okay, so this is the integer rectifiable current, and the general notion of current was more abstract. With the general notion of current, one had been able to define a notion of boundary. So once you had T, you can define boundary T of F pi 1 through pi m to equal T of 1 F pi 1 to pi m. The idea being that if you were actually looking at it as a form this way, and you took the D of this form here, so this is like boundary T omega is T d omega. If this is thought of as F d pi 1 wedge d pi m, and you took D of it, it would be 1 df wedge d pi 1 through d pi m. So this notion of boundary is defined just with the current. So of course you can apply this notion of boundary to integral current, and then you say an integer rectifiable current, integral current is T is integer rectifiable, and boundary T is integer rectifiable. So it has a nice boundary that's also a bunch of charts, but you don't actually get this boundary by taking the boundaries of each of these charts. It just doesn't usually work. And the theorem was that if you need only check that the mass of the boundary T is finite. So an example of an integer rectifiable current, say in Euclidean space, would be a set, say just a region in Euclidean space whose boundary is infinitely long. So that would be that would not be integral. So this is saying basically that all you worry about is the length of the boundary. All right, so something that I did not mention last time, was the notion of a restriction. So T restrict a function, so let's call the function H, H of F pi 1 through pi m. Actually, you can restrict to any tuple, but I'm just going to do a function, is T of F times H pi 1 through pi m. So this is called the restriction. Now, in general, when we first define these currents, it was required that F was Lipschitz bounded, and each one of these was Lipschitz. But then there was a locality properties and a number of other properties proven, which allowed us to take L1 measure T limits of these Fs. So that allows us to now define this on a larger class. So it's actually defined as long as F is L1 measure T, which means that you could take this H to be a rather not nice function. So this allows us to write T restricted to a set. Let's call the set capital H. This is a set H contained in the metric space we're considering of F pi 1 to pi m is equal to the T F times the indicator function, so 1 of H pi 1 to pi m, where 1 of H of x equals 1 if x is an H and is 0 if x is not an H. So even though this is not officially a bounded Lipschitz function, they defend that this is definable for the nice Borel H's. So now we have a notion of a restriction. So if you think of T as being like a submanifold, as describing a submanifold, and H is some set here, then the restriction is just this part of the submanifold. That's like the intersection of the set there. And this is useful, and in particular the Ambrosio-Kirchheim slicing theorem, which is the theorem that allows you to take an integral current and a Lipschitz function and start slicing it with the level sets of that Lipschitz function. It's a very complicated theorem, and it allows you to slice in many directions. But let me just say one implication. It implies that T restricted to BPR, where this is a ball, okay, is an integral current for almost every R. Almost every R. All right, so in any metric space Z, no matter how horrible Z is, the integral currents are nice enough in that when you take the balls intersected with them, although some level, the key problem here is not that it's rectifiable, but that it's integral, and that you want to make sure that the mass of the T intersected with the sphere is finite. That isn't true for every R. Some intersections with some spheres could be infinite, and there are examples, but almost every R, this will be nice and well-defined. So we're going to need to use that. All right, so now in joint with Stefan Wenger, this one is in the JDG paper, we have defined integral current space, and now we have all the theory we need from yesterday and today. So we have integral current space is a metric space XD, a metric space not necessarily complete, with a current structure, an integral current, T. Now, since X is not necessarily complete, we have T as an integral current in the completion, because Ambrosio-Kirchheim defined everything for complete metric spaces. So we have to take the completion of X in order to define this integral current T, and such that X is the set of T, which I'll remind you that the set of T is the set of points X such that the lim inf as R goes to 0 of the measure of B0 XR over R to the M greater than 0. So this is an m-dimensional, it's M and m-dimensional integral current. And then you have m here to get the positive density. Now this T, mass measure TBXR, this is actually the same. You should notice if you use this restriction, this is also the same as the mass of T restrict BXR. Okay, so this mass measure, using the measure for T of BXR is the same as the mass of T restricted to BXR, because in general, the mass of a current is equal to the mass measure of the whole space Z. And in this case, the mass of T restricted BXR would be T acting on the BXR. Okay. All right, so we have this nice collection of points, and we define the flat distance. Oh, let me give an example. M-oriented Riemannian. Then m equals x dt, where x is just the Riemannian manifold itself. X equals m. D is the infimum of lengths of curves between points. So, and the t acting on any omega is equal to integration over m of omega. All right, so the only place here where you actually use the metric is this infimum of lengths of curves. The t, this integral current structure, is just about the charts and has nothing to do with the metric. All right, so if you change your metric on this space, you don't change t. Are there any questions? All right. Then we have the definition of the flat distance, intrinsic flat distance between two is the infimum of the flat distance inside any z of the push forward of T1, push forward T2, where the infimum is over all complete z and phi i's from xi's to z that are distance preserving. And here, recall that the flat distance, d flat inside z, between any two currents, phi 1 number T1, phi 2 number T2, is equal to the infimum of the mass of A plus the mass of B, such that A plus boundary B equals phi 1 number T1 minus phi 2 number T2. And this is all now rigorously defined because we're using Ambrosio-Kirchheim's notion of integral currents. This A is an M integral current, and B is an M plus 1. And so we have a theorem which says that D flat M1, M2, if you think of this guy as M1, and this one as M2, then D flat M1, M2 equals 0 if and only if there exists a current preserving isometry. Oh. Yes. But there's one on the boards, right? What's the board like? M2 such that, and by current preserving I mean that the push forward of T1 equals T2. And I should say X1 to X2 here. So what this is capturing is that the classes that are here are not just integral current spaces, but current preserving isometry classes of integral current spaces. So that the opposite orientation is a completely different space. The isometry is the only part that's encoding the X1 D1 and the X2 D2, and then the push forward of the current structure. This forces orientation preserving. So in some sense, the things I was talking about in the first lesson, in the first meeting, are now rigorous thanks to ambrosial cure. Oh, I'm sorry. Yeah, for this one, we assume that they're precompact. The theorem.
Okay.
Sorry about that. Thanks for reminding me. Yeah. Yeah. It actually was quite important to the proof. Yeah, sometimes, yeah. We don't have a counterexample. We don't have a counterexample if they're not precompact. Just to be fair. So, open question. Okay. All right, so, yeah, so just to be fair there. Yeah. M1 is X1, D1, T1. I'm going to use the M to represent the whole thing, including all the information. The X will be the space of points. The D1 will be the match. It's just easier that way. Then most of the time I can just write M1, M2. Okay, so now in this definition, the infimum is over all complete Z. But we have a theorem which says that basically this infimum is achieved. So this is joint with Stefan still. Infimum is achieved. And once by a Z and an A and a B. In other words, both this infimum and that infimum all are achieved. Okay? This is when, again, M1, M2 are precompact. Okay, which is what we'll just stick to for today, okay? So when M1 and M2 are precompact, the infimum is achieved by Z and an A and a B. Now the A is an M integral current, the B is an M plus 1 integral current. So if we just take, and A and B are sitting inside Z, so we really can change, so let Z prime just equal the set, the support. of A union the support of B sitting inside Z, and that's all we actually need. That's a nice complete space because supports are closed. That could be our Z's that we took the infimum over. That could be the class of Z's. But A and B are integral currents, so this the class of possible Z primes is really just m plus 1 dimensional. So thus, the infimum in the definition of dF can be over metric completions of m plus 1 rectifiable, countably HM rectifiable. Let me write the whole thing out. Countably HM plus 1 rectifiable metric spaces because we can use the charts that we're defining B and the charts that we're defining A. And the A part will be HM plus 1 measures 0 anyway. So really only the B part is part of this notion here. In particular, they're separable, which is not in the original definition. Okay? So then, by Kuratowski embedding, is it I or Y? I don't remember. I'll Italianify it. It's an I. Okay. By Kuratowski embedding, by the Kuratowski embedding, we which says that you can take separable metric spaces into Banach spaces. The infimum can be over Z Banach. So again, in the spirit of lots of equivalent definitions for the same thing, so that each is practical in different settings, we have 3 effectively equivalent definitions here in the case when they're both precompact. So you can have all complete Z's, all complete separable Z's, or HM plus 1 rectifiable Z's, or Banach Z's. Okay. And each will be useful in different settings. Everyone fine? Okay, do you know, people know the Kuratowski embedding theorem? You basically map it into L infinity by taking distances from points. So the L infinity of Z. So you take Z to L infinity of Z by taking any point to the distance function from the point. And that turns out to be an isometric map. All right. So now, the first theorem, well, that's another theorem, but okay. Okay, we'd like to relate the intrinsic flat convergence to existing notions of convergence at this point. So one notion of convergence is to study the Lipschitz convergence if x1, d1, and x2, d2 are close in the Lipschitz sense. In what setting would these guys be close in the intrinsic flat sense? Now, that doesn't make sense because x1 and d1, the Lipschitz distance between 2 metric spaces doesn't involve the t, right? So the t, if the one guy is x dt and the other guy is x d5t, they can be arbitrarily far apart. You can make 5 bigger, k, multiple of t, just take it larger and larger. So they'll be far. So in this theorem, we're going to assume m1 and m2 are Lipschitz manifolds. Mi are Lipschitz manifolds. So that the t, the x1 di are the usual, as we said before, and the ti is going to be of the form integration over mi. All right, so then we have a very specific ti that's automatically enforced on you. All right, so it's weight 1, and we have this, so they're oriented Lipschitz manifolds. So if they're this, Then there's a Gromov-Lipschitz distance, which just basically coincides with Lipschitz convergence. And we said we proved that the flat distance between M1 and M2 is less than or equal to, I don't want to write out the whole messy formula, but, well, I might as well put the dimension, since people care about dimension here. So there's the dimension coming in. The lambda to the m minus 1, lambda minus 1. And then we have the volume, the sum of the volumes. So volume m where lambda is e to the d lip m1, m2. I know we're exponentiating back up, but that's needed. So the Lipschitz distance, which is Gromov's Lipschitz distance, is the one that involves logs of the lip constant. So d lip between m1 and m2 is equal to the infimum over all by Lipschitz psi from m1 to m2. Let me lift this up. Okay, so it's the infimum over the Lipschitz of the log. So it's a bi-Lipschitz map from mi2 of lip psi plus log lip psi inverse, which was defined in Gromov metric structures. Okay, so this is a distance, and it satisfies triangle inequality and all sorts of nice properties. And so we have a nice relationship. If the two manifolds are, in fact, Lipschitz close, there's a very precise formula relating these two. And on tomorrow, I will talk more about possibilities when only subsets of M1 and M2 are close in the Lipschitz sense, and they may have funny extra strands in one of them or something. But this is all we did in our original paper. So we have this nice control. Yep, any questions? No. Again. Yeah, that's kind of funny, but if they're bi-Lipschitz close, the volume of M1 and the volume of boundary M1 are very close to the volume M2. Yeah, so you could think of, if you want, you could make it some volume M1 plus volume M2 plus volume boundary M1 plus volume boundary M2 if you feel like it. If you like that, I think it's a lambda plus 1 that's supposed to be there. Where I wrote the lambda 1 plus, the reason that, the scaling, the fact that there's two different scaling is why there's the lambda minus 1, which I think should be a plus 1 up there. Now, there's two proofs of that. The proof in the paper with Stefan is using very much ambrosio-Kirchheim theory, but Sajjad Lakhsian, who's around here, not in the audience right now because he knows all this, but we together proved pretty much almost the same result, but using an explicit construction of a z that was one dimension higher. Oh, I'm missing them. Thank you, Raquel. Okay, the other expert in there. You're right. Somebody has to pull that down because that one I can't leave out. And I'll put this as a plus 1, right, Raquel? Yeah? It is minus 1. Okay, good. Okay. Times, you have to have grad students to keep track of life, right? Maximum diameter M1. This one? Which I guess is also close anyway. Times, yes. This is part of this equation. Multiplied. That helps because it wasn't scaling, right? Okay, anyway. Okay, so a very similar theorem with slightly different constants is proven with Sajjad Lakhsian to study manifolds, and in the proof with Sajjad involves constructing a very specific Z that's actually in this class. And it has a nice, very precise property, and I'll draw the picture of that tomorrow, because that proof, the reason we did it was because we also wanted to study the cases where they're not Lipschitz closed globally, but only on subregions. So we reproved the theorem. This theorem, the way it's proven with Stefan, definitely required a global closeness. Every single, this map. We needed a bi-Lipschitz map from the whole M1 to the whole M2 for this argument. So tomorrow I will talk about one where you only have subsets that are close. So constructive proof. This is an AK proof. AK meaning ambrosial hymen, right? Okay. All right, so now I can erase this. All right, so let me talk a little bit about Gromov-Hausdorff convergence again. This is useful facts, and they've sort of been hinting at some of these Gromov-Hausdorff properties in some of the other talks, but I just want to make them very precise. And then I'll talk about to what extent we have the same kind of properties with intrinsic flat convergence. So recall Gromov has proven the following, okay? So remember, he has the Gromov-Hausdorff distance, which we all know very well now, right? So one of his theorems says that if xi di converge in the Gromov-Hausdorff sense to x infinity d infinity, and they're all compact, so our flat distance involved taking infimum of the dfc's, and remember the Gromov-Hausdorff distance involved an infimum of Hausdorff distances, and he proved that his Gromov-Hausdorff distance was 0 if and only if there was an isometry between the spaces. So, but the actual definition involved, so let me just write this here, B flat M1, M2 is infimum, right, FZ, push forwards. And the Gromov-Hausdorff had Hausdorff here, right? And the infimum was overall z's and phi i's that were distance preserving. So the infimum is the same infimum in the Gromov-Hausdorff definition. This is the Hausdorff distance. So what's interesting is he proves that in the compact setting that this is in fact 0 if and only if there's an isometry between the spaces. But he proves here that if they're all compact, then there exists a common zi, common compact metric space Z and maps, distance preserving maps, phi I from xi's to z, such that the Hausdorff distance of the phi I xi's, phi infinity x infinity, goes to 0. So although the original definition was that you take the Gromov-Hausdorff distance and there's a z for each pair, x1, x infinity, x2, x infinity, x3, x infinity, he actually can trace as a single compact metric space z that all of them can be placed into. And this was discussed, for example, in Gigli's talk, where he emphasized that, yeah, it's a common z, but he wanted not to worry so much about the Hausdorff convergence, but the measure convergence of these guys, right? So this common compact metric space z is exceedingly useful. And this allows us to define things like to take pi in xi and say pi converges. I don't want to take up so much space here. And say pi converges to p infinity if phi I pi converges to phi infinity p infinity. And this will depend on the choice of the phi i's. You could have some sort of rotation in the limit. So this doesn't quite make a unique p infinity, but it does up to a certain amount of isometry. You've got your notion of pi is going to p infinity. The fact that Z is a compact metric space means that actually, if I take any sequence pi in xi, then I have a subsequence of the pi's which will have a limit by Bolzano-Weierstrass theorem on Z. So that's a really, really powerful theorem. Also, we have that if there's p infinity, in x infinity, there exists pi in xi such that pi's converge to p infinity in this sense. All right? Now, the Bolzano-Weierstrass theorem that one has automatically because Z is compact is not going to hold in the intrinsic flat setting because we do not get this full-strength theorem that Gromov has. On Friday, I will tell you the Bolzano-Weierstrass theorems and Arzeli type theorems that exist in that setting, but everything is harder because there is no compact Z. However, even though we don't get a compact Z, in the paper we do get a common complete Z. If xi flat, sorry, I should call them mi flat to m infinity, all precompact, there exists a common complete metric space separable, countably hm plus 1 rectifiable metric space C. And phi i's from the mi's to Z such that the flat distance inside this Z of the push forwards of the TI's goes to 0. So we do have a common space, but it is not compact. In fact, it pretty much is not compact in almost every interesting case. All right? Because the most interesting cases for flat convergences are the settings where there is no Gromov-Hausdorff limit. So in those settings, if there had been a common compact metric space, then you get a Hausdorff limit and then so on. Okay, so we have this common complete separable countably hm plus 1 rectifiable space Z. Now, we have the Kuratowski embedding theorem, so what does that give us? Z could be Banach space. Very useful. Exceedingly useful. Okay. The way this is proven is using the fact that this is actually achieved. And so we had the Z's that were countably hm plus 1 rectifiable, and then we glue them together in a way that allows us to control everything. Now remember that our integral current spaces also include the 0 space. Okay, so our integral current spaces include the 0 space, and when we're talking about the 0 space, just consider the TI's or the T infinity to be 0. So we're just saying comparing the current 0 with the other current. So it's all fine. we have no hope for Hilbert. Okay, but Banach is pretty good. All right. So we have this, we can at least make Z Banach. Now the nice thing about Z Banach is that this work of Wenger about currents, it's about the Ambrosio-Kirchheim kind of currents on Banach spaces. Okay, so that's sort of his world where he was the expert already. So he had been studying these currents on Banach spaces, and he had shown that in Banach spaces and slightly more general spaces, the flat distance, say, or Banach space is Z. Although to be honest, people usually write E, but anyway, when it's a Banach space, the flat distance in Z between a sequence Tj, T infinity goes to 0 if and only if Tj converge weakly to 0 to T infinity. This is assuming that the mass of the Tj's is uniformly bounded and the mass of the boundaries is uniformly bounded. So remember I mentioned that Ambrosio-Kirchheim had the same, not Ambrosio-Kirchheim. Federer-Fleming had this result in Euclidean spaces. Ambrosio-Kirchheim had not gotten this result in their paper. And that's because they were considering complete metric spaces Z. You really needed the Banach spaces to pull this off, and he uses some really neat filling. He really can control the system. Then it ends up to be on metric spaces pulling back with the Kuratowski. Okay, so then pull back. Using Kuratowski. To our common Z, right? So in some sense, I'm writing this for historical reasons so you understand what was done. This is a previous paper of Wenger's that was not worrying about the general case. I know. You know what? We always just go over to Kuratowski when we need. Let me not say pull back. Let me just say use Kuratowski whenever you want to use this. That's how I should say it, okay? I don't want to say pull back using Kuratowski because it's complicated and messy. So let me just say we make Z Banach whenever we want to use this. Okay. Banach Z. So in other words, we'll use the Z as nice like this when we want to. We'll use the Z as Banach when we want to. We'll go back and forth as we need, and everything works out nicely. All right, so what are the consequences of this? There's a number of consequences thanks to all the things that Ambrosio-Kirchheim proved. Okay, so we've constructed this common Z that has all these nice properties and could be Banach, and we have Wenger's old theorem about flat and weak convergence. So this allows us to use various Ambrosio-Kirchheim theorems to combine information. So one of the consequences is that we have lower semi-continuity of mass. From AK, lower semi-continuity of mass. Okay, so I had mentioned that Ambrosio-Kirchheim had proven that if a sequence of currents converges weakly to a limit current, then the masses are lower semi-continuous. So what we have, by taking our theorem, we put them into the common space, and then we move it over to a Banach space, and we have the weak convergence, and so we get that the masses are lower semi-continuous in the sense that if xi, di, ti flat converge to x infinity, d infinity, t infinity, then the mass, the limit I to infinity of the masses of the ti's is bigger or equal to the mass of t infinity. So keep in mind that one thing about the mass was that if you push forward it by distance preserving map, the mass was the same before and after you push it forward. Okay, so we push forward these masses over phi number ti's, and there the mass is the same over there, and then we push it into the Banach space, we get the weak convergence. So this limit is the same as the limit for the push forwards, which is bigger than the m of the push forward, which is equal to the masses. Okay, so this is exceedingly useful because we now have some sort of notion of what is happening to volumes here. Right? We should also say, and we need to assume, mass Ti, that's some constant, mass boundary Ti, that's some constant. We need that condition in order to have this equivalence between the weak and the flat. All right, so that's one of the most important properties. It also, this can be localized. So in fact, since we can say viewing BPIR as an integral current space, so this is a ball inside the space, which is true for almost every R, that we could do that. Look at a ball and think of it as integral current space. We have that the limit as I goes to infinity of the masses of the balls is bigger or equal to the mass of the limit ball. This is almost every R, because they're not even defined otherwise. And this is if the PI's go to P infinity. Right? So we are not getting metric measure convergence. Metric measure convergence would give us that the masses converge to the masses. But we're getting this lim-inf situation. All right. Another thing that Ambrosio-Kirchheim proved was that the if Ti converges to T infinity weakly, then the boundary of Ti converges weakly to the boundary of T infinity. So we have, under the same conditions, if Mi flat to M infinity, then boundary Mi flat to M infinity, boundary M infinity. And actually, this one doesn't even require the uniform mass balance. And And so we have the limit of the eigeninfinity of the boundary masses which in general you wouldn't control boundaries very well with Gromov-Hausdorff or a metric measure. There's really no even definition of boundary in those settings. And also on the ball level. So these are very useful. Now, I don't have time really to present all this in detail, but one also gets the Gromov, the Philvals, that the limit, as I goes to infinity, of the Philval, we'll call it Philval infinity. It's a filling defined using Banach spaces. Philval infinity of boundary BPR, PIR, converges exactly to the Philval infinity of the limit. Okay, so this is a slightly different Philval than the Gromov filling volume in the sense that the fillings are integral current spaces instead of they're integral current spaces instead of what he used chains, and the masses are the masses of ambrosial Kirchheim, which is weighted differently than the way Gromov weights. So we have the different lambda factor. Okay, so it's slightly different than that, and so we put a little infinity on it just to make it slightly different from Gromov. But the fact is, a lot of Gromov's theorems about Philval just carry over to this kind of Philval. There's really no the lower bounds and things. So this is one more thing, and this is not in the JDG paper. This is in the CVPDA paper with Finger. Okay, so we have two papers, the JDG and the CVPDA paper. All right, so more information about this is in a properties paper, CF, archive with Portuguese. So we clarify quite a bit what this exactly means in the paper with Portuguese, and we also describe things called sliced filling volumes and other notions, new notions of filling volumes that can be defined using slicing theorems. So just a tiny hint about this stuff. I'm not actually going to ever talk about this paper this week, but it does exist. All right, so let's get back to more basic things. Thank you. He's paying attention, you're not. You were still thinking about the Philval. I know. It's fun stuff, but it's not enough time this week to do everything. But Portuguese is in Germany, so you guys can invite him to give a talk. Also, he's working with Joost. And he also has studied the case where you happen to know that the integral current spaces have the masses converging. So if you apply that as an extra condition, that you have your flat convergence and the masses converge, in that setting, he controls the masses of the balls inside as well. Those end up being equal. So there's no inequality. Those are equals. And he proves the eigenvalues are lower semi-continuous. So he has a lot of very nice work. Okay, so back. So going back to the first paper again. All right, so so far we have this lower semi-continuity in mass because we have this our embedding theorem, right? So we say that the flat converge all precompact, common complete metric space. More consequences of this now. So we've talked about filling volume, we've talked about masses, but let's go back to what else we have as a consequence of this. So we, let me just think about this. Yeah, okay. So now I want to talk about GH convergence versus flat convergence. All right. So there's an immediate theorem. So in our paper, we kind of attribute this to Gromov and Ambrosio-Kirchheim. Gromov plus Ambrosio-Kirchheim. Which says that if xi di gh to x infinity, d infinity, precompact, let me put these on this. And mass ti less than constant, mass boundary ti less than equal to constant, then a subsequence converges xi di ti. Sorry, I should say that, right? So that the xi di ti's are integral current spaces, right? We need that. Flat converge to y d infinity t infinity, y infinity, where y infinity is a subset of x infinity and d infinity is restricted. So I mentioned this in the first day, that this theorem was true. That you always, if you had a Gromov-Hausdorff limit, you ended up with a flat limit of a subsequence, and the flat limit would sit inside the Gromov-Hausdorff limit. And I had those pictures of the spheres with the thin tube, and I said the Gromov-Hausdorff limit was the two spheres with the geodesic, and the flat limit was just the two spheres. So this is the actual theorem. Now you know all the ingredients, and you can understand where the proof comes from. You have the Gromov embedding theorem, which says that as soon as you have the Gromov-Hausdorff limit, right? Gromov embedding theorem gives you Gromov-Hausdorff limit. Says that they all go into a common compact Z. Now they're sitting in this compact Z, and the push forwards have the same mass bounds. So Ambrosio-Kirchheim compactness theorem says a subsequence converges weakly. Now we push it over with Kuratowski to a Banach space. Subsequence converges weakly there. Flat equals weak convergence. And then we pull back and we've got the flat limit. But what we've got is this weak convergence to like a T infinity. So when you draw the picture, I'll draw the pictures. So the first thing you do is you put it into Z, right? Yeah.
This X infinity, so we suppose that is an intrinsic flat space.
No.
Is it the mass?
No, it might not be.
It might not be, but it's the mass bounds are the things that stop, say, things from collapsing, or?
Yeah, let me do the steps of the proof. I'm going to draw the proof. So you have, we have this first condition here, right? The GH convergence. So by Gromov, there exists common compact C. So we're inside this big compact C. This is my Z, right? And I have the images, phi I m i's, sitting, xi's. They're sitting in Z. And they converge to something. They converge to phi infinity, x infinity. All sitting inside Z. Nice, well behaved. All right, and they're Hausdorff converging. And Z. Now we've got our currents. The currents so now we push forward I number Ti are now currents in Z. Okay, exactly equal to this images here. Okay? Phi I number Ti. But the currents could have cancellation or collapse. So I am not drawing the image of the currents yet. Okay? We do know, however, that the mass of the phi I number Ti's is equal to the mass of the Ti's, is less than a constant, and that the mass of the boundaries okay, because the push-forward maps are distance-preserving, so the masses are preserved, right? So you have that. So now these phi I Ti's are sitting inside a compact Z, and they have these bounds, so now we apply mbrosial-Kirchheim. Get some S infinity. So phi I number Ti's weakly converge to some S infinity. And S infinity is here. This is the set of S infinity. Okay? This is subsequence. In the case with the two balls and the thin tube, the phi infinity x infinity looks like two poles with a line segment, and the set S infinity will just be the two balls. Okay, so it's sitting inside. And we do a little work to show that it actually sits inside phi infinity x infinity. I need to erase. Even though we're about to use this. All right, so we've got this subsequence that makes a set S infinity. And with a little bit of work, we show that set S infinity is a subset of phi infinity S infinity. This is not hard. Just not hard. In fact, the support is contained. Okay? Just a little work to do that. All right? And that's, so you do that, and now you've got this phi infinity. You've got this S infinity. And now we want to use the flat and the weak agreeing. So we take Kuratowski, and we move to L infinity of Z, which is Banach. And I don't know what we want to call the Kuratowski embedding, eta or something. So we have eta following phi I number of the Ti's is weakly converging to eta following phi in eta push forward of S converges weakly, and then there's flat convergence inside the L infinity Z of these guys, then that gives us d flat of xi diti to this set of S, d restricted from z, S goes to 0. So it's a very constructive proof. This is the limit space. So that's the end of that proof of that theorem. Is time up? Yes. Right? Yeah. So this is the QED. All right. Thanks.
Are there any questions?
Oh.